Hello guys, welcome back to Maison African Motives, still on Mechanotechnics and form, working on metal cutting machines. We are going to be revising the question paper, which was written in August 2021, which is a bit familiar to the question paper that we had of August 2016. If you check this first part of the question, the 7.1, where we are given a lathe is driven by a motor providing a maximum input of 3 kilowatts at a speed of 1,500 revs per minute. At maximum power, the machine efficiency is 80%. So given efficiency of the machine, and also the maximum and minimum velocities, which is the speed of the lathe, are 3,600 revs per minute, and also 40 revs per minute for the minimum speed, respectively. Find the torque at the maximum power. Okay, so this part, I'm just going to explain a little bit. Since we had this question from our previous paper of August 2016 that we had. Okay, so here what we are given, if you are to check or if you are to take this properly, guys, we are just given a normal formula that we are supposed to take into consideration for torque. Okay, so remember that from our power, explain this, that power is equivalent to 2 pi nt over 60, which we can actually formulate to make t the subject, because this is same as over 1. So we can just cross multiply here. 1 times 2 pi nt, this is going to be 2 pi nt, which is equal to 60 times p, that is 60p. So to find n, we can simply divide by 2 pi n both sides, by 2 pi n both sides, so that we can have the t. So the t that we are going to have representing the torque is going to be given as a 60p over 2 pi n, which this part depends with the information that you're working with. Okay, on the first part, we are given the input conditions. Okay, so here I'm just going to say 7. Okay, 7.1, it's fine. So on the information that we have the input power, the maximum input, which is 3 kilowatts. This is the input power. So you're given Pn of 3 kilowatts. At the speed, at this speed or velocity of the input, again, which corresponds with this, I'm just going to have in, and this one as in, which is at 1,500 revs per minute. So these are the conditions that we are being asked to find at the first part of the question. Here, the question is asking us to calculate or to find the torque of the maximum power, but on a condition that we are at the driving shaft of the motor. So at the driving shaft, that is at the input of the motor, at the input. So at the input, that is where we have this information. At the input, we have got P in and N in at the input. So this is the one that we are going to use. Okay, so here we are going to have that's 7.11. So our T, like I formulated here, that our T can be given as a 60p over 2 pi n. But we are talking about the input here, the input power at the input speed that corresponds. So we are going to take this information as it is. So this is going to be P in, and this is going to be N in. So from this, we can calculate our T, because we are given the input power of 3 kilowatts. That's 3 times 10 to the exponent of 3. And also the input that corresponds at that power of 1,500 revs, which is the speed. So with this information, we can calculate our T. So that will be the torque in this case from this formula is going to give us 19. So this is going to be 19,08. That's 0.985, which is going to be 0.99 to 3 decimal places Newton meter. All right, so this is how we can calculate the torque depending with information that you're given. If you check on the 7.12, it's another information that is different from the first one, because we are now at the driving spindle of the lathe, meaning to say this is at the output of the motor, because that is the driving of the lathe there, at the maximum velocity, which is at the maximum speed. And we have here at the output. And also remember, from this, we have got the maximum and minimum velocities at. All right, so let me take these velocities and also the efficiency that we are given. All right, so we are given the efficiency in this case here. All right, so that is the 7.12. So remember, we've got an efficiency of 80%, and the speeds, okay, as a decimal, this can be 0.8, okay, 0.80. But here, if you check, we've got the maximum here, the maximum and minimum velocities. These are the speeds. So we've got the speed here of 3,600 maximum, 40, which is minimum. All right. So our any max here, we can just write any max and any min. Okay. So our any maximum is at 3,600 revs per minute, which is the maximum velocity, and the minimum velocity, of which we do not need this for now, but let's just write the minimum is at 40 revs per minute. So this is at 40 revs per minute. And from the input power that we had, because remember this time we said we are working at the output, meaning to say we are going to use the formula for output. This formula is not going to change. We are going to use this formula, but what is going to change is this P and this N. Remember, from this formula, we said our torque can be given as, okay, let me write our formula here. Our torque can be given as a 60P over 2 pi N. But take note, we are dealing at the output, the driving speed, at the output there, where we are supposed to have this as the output and this as the maximum. Okay, we are given at the output, but at the maximum speed, maximum velocity. We are at the driving speed, which is our output, but at the same time at the maximum velocity. So don't forget that we are dealing with two things here: the output power, but the speed has to be maximum. So where are we going to have our maximum output power now? We are going to obtain from the efficiency, because we know that efficiency simply is power out over power in. Having an efficiency of 0.8, we don't need the 100%. That's why I'm ending here. So I'm going to use this 0.8. So 0.8 is equal to P out, which is the one that we are supposed to calculate, over P in. Our input power, remember, it was at 3 kilowatts. From this information that we had before, the input power is at 3 kilowatts. So this is the one that we can use to calculate the output power. So you can simply cross multiply 1 times P out, that is P out is equal to 0.8 times 3, so it's 3 times 0.8, which is going to give us 2.4. So you're going to obtain 2.4 kilowatts. Or you can convert the kilowatts to watts, which is 3,000 watts. 3,000 times 0.8, which is going to be 2,400 watts, or just 2.4 kilowatts. Okay. Having the output power, we can be able to calculate our torque, because we are saying it is equal to 60 times the output power of 2.4 kilowatts, which is 2.4 times 10 to the exponent of 3 over 2 pi n, which is 2 pi times the n max. And our maximum here is at 3,600 revs per minute. So this can give us the value of T, the one that corresponds with this information, which is at 6,36619, which is going to be 66 in this case, Newton meter. All right, so that is the torque that you're going to have in this case for this condition. If we are to consider the other part of the information, we are now given that it must be at the driving spindle again, which means we are still at the output, the driving spindle, we are still at the output, but this time at minimum velocity, at minimum speed. So meaning the power that we calculated before is not going to change. This power, our output power, is not going to change, all right? But what is going to change is the speed, okay? So let me just have it here. So this is 7.13. So our torque also, the formula is not changing, 60p over 2 pi n. The only thing that we are supposed to consider is this time we are told at the driving speed, which means we are dealing with the output power, but at the minimum speed, the minimum velocity. So we are working with the minimum velocity there. All right, so let us have our information. That's T is equal to 60 times the output power of 2,4 kilowatts. That's 2,4 times 10 to the exponent of 3. Everything over 2 pi n times the minimum speed that we are given as a 40 revs per minute. So we are going to use 40 revs per minute. So this gives us the torque in this case, which is going to be 572. So we've got 572,9577, which is going to be 958. All right. So that will be 958 to 3 decimal places, and that is a Newton meter, the units there. All right. So this is how we can have our question. So as you can see, these typical questions, all you need is to know the proper formula to apply and how to apply that formula in a proper way. All right, so this is what we had on the 7.1. If we check on the 7.2, we are now given the other part of the question, which is to calculate the power in kilowatts. And take note, they gave us an instruction here in kilowatts. Consumed by, so we've got this information. So let's start with the first part of the question, that is 7.21. Okay, so let me just have it here. So we need to calculate the power, but this power is supposed to be in kilowatts. Okay, so on 7.21, we are given a shaping machine operation in which the cuffing force is 1,200 newtons. So there we have got the force of 1,200 newton. And the stroke length, take note of the information that we have. We've got the length, which is our stroke length of 275 millimeters, which we can convert to meters. Divide by 1,000. This will be 0.275 meters. And it takes 13 seconds to complete. So we are given the time in this case. It takes 13 seconds. So there we also have the time in seconds. So guys, when you are given these types of questions, you answer according to the information that you are given. Which formula is best to use to calculate the power in this case from this information that we have? We have got the force, we've got the stroke length, and the time. Whenever we've got time, the formula that we are supposed to think of is of the work done, because it is only the part that we have got work done over the time taken in seconds. But how can we have the work done now from this information? Remember that work done is equivalent to force times distance. All right, so this is supposed to be force times distance. But which distance are we considering? That is our stroke length in this case. So in this case, our formula can be force times the stroke length, which is L. So this is the formula that we can simply use to calculate the work done. So if this is the formula for work done, so it means we can calculate the work done, or we can just substitute into the formula, because we are saying our power can be written as work done over time taken. This is according to this information that you have. And the same work done that we are talking about is force times distance, which is the stroke length. So I can write this as force times stroke length in place of the work done, because this work done, we said it's force times distance. But everything has to be divided by the time now to find the power. So this will be your formula for power. Force of 1,200. So we've got 1,200 times the stroke length of 0.275. 275. Make sure it's in meters. Everything divided by the time taken in seconds. That is going to give us the power. Remember, this will be in kilojoules per second, meaning to say we are in watts. So our answer is going to be 25,3846, something like that in watts. But take note, this power is supposed to be in kilowatts. That is per given instruction. So to convert to kilowatts, we can simply divide by 1,000. That will be our answer is now in kilowatts. So if we divide by 1,000, this will be 0.025. That will be in kilowatts in this case. All right, so this is how we can have our final answer in kilowatts. Divide your answer, the one that you're having, by 1,000, or you can multiply by 10 to the exponent of -3. All right, so that is how we could have calculated the force from this information. If you take note, is the same thing on 7.12. You can just remove this information. This is another question, actually. This time we are given to calculate the same power in kilowatts as we are given the same power in kilowatts. But this time we are given that this is a lathe operation during which the cutting force applied to the cutting tool is 1,000 newtons. So given the force applied to the cutting tool, which is 1,000 newton. The rotational speed of the workpiece with the diameter. So you've got the diameter there, which is 350 millimeters. You can convert to meters, divide by 1,000, 0.35 meters. This time we have got the speed of 350 revs per minute. If you consider this, it is the same question that we had from the November, it was actually August 2016, where we had the force, the diameter, and the speed, and we wanted to calculate the power from there. There are actually so many ways that you can actually use to calculate the power whenever we've got information of this nature, or whenever we've got this information that we have. Okay, how can we calculate power from this? Okay, let's start with this formula that I used in our previous part for the August 2016 paper. Remember, I said power can also be calculated from 2 pi, and in fact, we talked about this on the first part of the question, 2 pi nt over 60, where t represents the torque, that is the force times the radius or the perpendicular distance. So meaning to say, with the torque that we have, or that we can calculate from the force times radius or force times perpendicular, we've got the force and we've got the diameter. So this is going to be force times radius, which is simply the force of 1,000 Newton times the radius, which is taken as the diameter over 2. So this is going to be 0.35 over 2. Diameter, you divide by 2. So this is going to give us 175 Newton meter. All right. Having this T as our torque in this case, therefore, we can calculate the power, which is from our formula that we wrote here, that power is equivalent to 2 pi times n, which is the speed of 350 revs per minute, times the torque in this case of 175 divided by 60. We can have our power. So this is going to be, if we divide properly, we are going to obtain our power as 6414,085 in watts. So remember, our power is measured in watts, but we have a specific instruction that we are supposed to follow in kilowatts. So how are we going to convert to kilowatts? If we've got this power in watts, we can divide by 1,000 or times 10 to the exponent of -3. This is going to be 6,414 in kilowatts. Okay, so this is what we could have done to have our power in this case. Okay, but also remember that power is also a product of force and velocity. Remember that. Okay, if power is a product, so this is what we can have. Actually, we can use this force times velocity. But where can we have the velocity, this part now, the velocity? Where can we have this from? Okay. Remember that velocity is simply taken from this formula. Remember that V is equivalent to pi dn, where this d is in meters diameter, n must be in revs per second. But if you are given the revs per minute, therefore we divide by 60 to convert. That is for a conversion to revs per second. All right. So this is over 60. So meaning to say we can calculate this V that we need here by this formula. So meaning we can simply substitute our formula. P is equal to F, which is the force of 1,000. So this is going to be 1,000 times our V. And this V that we are talking about is the same V that we said is going to be pi dn over 60. So this is going to be pi times our d, which is the diameter of 0.35 times n, the speed in revs per minute of 350. But this is supposed to be over 60 to convert this. All right, so this is the part of having our speed. But we can convert, we can substitute back into the formula for V. In place of V, we are now substituting our V here using the information that we have. So this gives us the same power that we had before. So this is going to be 414, something like that in watts. Then we can convert to kilowatts, 6,414 in kilowatts as per instruction of the question. The question is asking us to leave our answer not in watts but in kilowatts. Okay, so these are the typical questions, guys, that you might have on metal cutting machines. Just have to revise more question papers or more revisions to prepare for the exams ahead of time. But for now, that's it, guys, from Mechanotechnics African Motives. Till we meet again.